So today we are going to discuss about free energy of regular solution. So regular solution, first we have to understand what is regular solution based on change in enthalpy during mixing of two binary solution or multi-component solution. So if we consider the ideal solution and then for a particular phase, suppose G alpha, we used to get is equal to XAGA plus XBGB and plus RT ln XA plus RTXB ln XB. So again I am repeating. What we understood that G alpha is equal to XAGA. XA is the mole fraction of A component or A element, and Ga is the mole component of A, is the gives energy of A, and XB same way the mole fraction of B, and Gb is the gives energy of B component, and then we are incorporating with T into del S, and del S equals to RT that R XA ln XA plus R XB ln XB. So in this way we understand for an ideal solution G is equal to, in this expression, what we hold. So this is for ideal solution. So what is the criteria for ideal solution? What we understood that for ideal solution del H mix is equals to 0, means that there is no change in enthalpy for mixing if you are talking about ideal solution. This is a big assumption. This is nothing but assumption. But however, in reality, what is happening, mixing is maybe endothermic or maybe exothermic. Sometimes heat can be absorbed, sometimes heat can be released. So based on that, the process can be represented as a endothermic process or exothermic process. So now we understood that the simple model of ideal solution cannot represent the scenario what we are just few minutes ago discussing, that mixing can be endothermic or exothermic. So for that, the model of ideal solution should be extended in order to include del H mix by so-called quasi-chemical approach. This quasi-chemical approach is a one kind of method where you are talking about certain probabilistic way to understand the behavior of chemical process. Now, if you talk about del H mix, it comes from what? Del H mix is due to the bond energies between adjacent atoms. So we are now extending the ideal solution to a scenario where we are going to incorporate del H mix, and that del H mix we are thinking, or we are assuming that it is due to the bond energies between adjacent atoms. So now what we say, that moment is not ideal. So non-ideal solution, the one of the simplest approach, because all this, whatever I am talking about a free energy of a solution. Now we are going to understand that del H mix and all those things. So how do I measure in terms of, if I want to measure the del H mix? So del H mix, if you want to measure, then you can do that. Suppose you can take A and B metals and you can mix them and then do DSC. That through DSC experiment, if there is a positive interaction or negative interaction, you would see in terms of what is called heat of formation. So heat of formation can be measured using DSC process, differential scanning calorimetry process. And if you use DSC in principle, one can do that and you can identify the heat of formation or measure the heat of formation. So large number of people who believe that in order to measure the delta mixing, from that we come to know that whether they are intermediately compound forming or they are having a repulsion because of there is a certain kind of phase separation. These are the possible ways or possible phenomena can be occurred based on how one atom is interacting with the another type of atom. Means suppose atom A is interacting, how it is interacting with the atom of B. So that is very important now, and that actually talks about how you are extending ideal solution to a scenario where del H mix is not equal to 0. What does mean by del H mix is equal to 0? Means the A atom does not repulse B atom as well as does not attract B atom. But here the scenario is that A atom can repulse or can attract B atom. So that's why the del H mix part should be present or should be considered. So in this scenario, if you check in the figure that there is A and B atom randomly distributed, and there are three types of bond can form. If you see the schematic diagram of the binary solid solution of the structure, three different types of interatomic bonds you can find out. That can be A bonds, and A bonds each with should have an energy. A bonds should have a bond energy, and that bond energy, if we name EAA, there will be a BB bonds, and BB bonds each with an energy EBB. And if you see AB bonds, that also each with a energy EAB. We are now getting the three types of bond and correspondingly three types of energies: EAA, EBB, and EAB. Now, based on that, if you want to understand that what is actually the process, how the assumption is going to change, the important statement already I have mentioned. You should remember that here in this quasi-chemical approach, it is assumed that heat of mixing del H mix is only due to the bond energies between the adjacent atom. And for this assumption, if you want to get the valid, you want to have the validity of this assumption. For this assumption to be valid, it is necessary that the volumes of pure A and B are equal and do not change during the mixing. Then only you can get there, so that you can get that the interatomic distance and bond energies are independent of the composition. So in order to get such a scenario where you are talking about del H mix is only due to bond energies between adjacent atoms, then you have to find out such a scenario, such a position, such a condition, so that the assumption will be valid. What will be the supporting considerations? Those are, one is the volumes of pure A and B are equal and they do not change during the mixing process, so that the interatomic distances as well as bond energies are independent of composition. Now if you see the picture, and then you can understand that from the schematic diagram, that AA bonds each with an energy EAA, BB bonds each with an energy EBB, and then you can go for AB bonds is energy with EAB. Now, if we now we want to find out the internal energy of the solution. That solution, now the solution is a solid solution having A and B both type of atoms, and they are distributed in certain fashion. Now we want to know the internal energy. So in order to get that, first what you have to consider? You have to, by considering zero energy to be the state where the atoms are separated to infinity, it is EAA, EBB, and EBB and EAB are negative quantities. Again, I am repeating. to infinity, when the atoms are separated to infinity, then what will have EA, EBB and EAB negative quantities and become increasingly more negative as bonds become stronger. Because when bonds become stronger, we used to relate that constant to the stability of that particular compound or particular molecule or particular substances. So the negative bond energy should be more negative, value will be higher, but negative in sign. That should be the case. Then the internal energy of the solution, that E, will depend on the number of bonds of each variation, each type, PA, PBB and PAB. If you see, PAB, PBB and PAA are the number of bonds of each type. Now, how it is related to del H mix, that we have to find out. So, next consider, before mixing, pure A and pure B contains only either AA bond, and in case of pure B, only bonds. So there is no AB bond when there is no mixing. So before mixing, there is only pure A and pure B. So there will be only AA and BB bonds respectively for the pure A and pure B. And by considering the relationship, if we are going to consider the relationship between PAA and PBB and PAB among them in the solution, we can show or we can say that change in internal energy on mixing, it should be given by del H mix equals to PAB into the energy, that epsilon. And what is that epsilon? Epsilon is equal to EAB minus half of EAA plus EBB. Means, but try to find out a difference in the energy, that is epsilon. Epsilon is the difference between the AB bond energy and the average of the AA and BB bond energies. So now again we want to find out, okay, this is correct. Now we have to get, if you want to go back to ideal cases, ideal solution scenario, what we have to do? We have to take epsilon equals to 0, and that leads to del H mix equals to 0. Then again you are getting the solution becoming ideal. So if the bond energies of EAB is equal to the average bond energies of AA and BB bonds, then scenario again comes to a condition where ideal solution behavior prevails. So in this case, the atoms are completely randomly arranged. That is a very important physical or physics-based interpretation of such mathematical expression. What is that? The atoms are completely randomly arranged. And the entropy of mixing, if you want to understand, then what will be the entropy of mixing in such kind of cases? That is PAB. We have to find out for that PAB, because the number of AB bonds, and what will be that? Is the Avogadro number multiplied by Z, Na or N Avogadro number multiplied by Z. Z is the number of bonds per atom and individual mole fraction A and B components, XA and XB. If you do that, then only you can get the number of possible AB bonds. Now think about if epsilon is less than 0. The atom in the solution, what we will do? If scenario is like that, we understood that epsilon is equal to 0, then del H makes equal to 0, then what will happen? It actually returns to the concept of ideal solution. But now we are talking about if epsilon is less than 0, then what will happen with this mathematical expression and corresponding physical interpretation or physics-based interpretation? If epsilon is less than 0, the atoms in the solution will prefer to be surrounded by atoms
opposite type. You should understand that opposite type of atom should be surrounded, because then only the more stability of the system are going to achieve, and this will increase AB bond number, PAB will increase. So if there is epsilon is less than 0, then what is the favorable condition? More number of AB bond will be generated, because then only we are going to get more stable configuration of the solution. Just now we are going to talk about just the first condition. Whereas if epsilon is greater than 0, just reverse condition, then what will happen? PAB bond will tend less in number, and what will happen will tend to be less, and then in a random solution. So complete randomness will be lost. So certain kind of pure A bond will be preferred, sometimes a BB bond will be preferred. So this is the very important concept, that epsilon, what is epsilon? It is the difference between AB bond energy and the average of AA and BB bond energies. It is very vital to understand which kind of bond formation will be prevail in a solid solution. It's very important. And if you now you can understand that del H mix, if you name one parameter, interaction parameter, that tau XA into XB, and it is equal to NZ epsilon. N is a Avogadro number, Z is N is Avogadro number, and Z is the number of bonds per atom. Already I told. Now, if you want to relate with the impact is really of respect to solution, real solution, then what you have to do, we have to introduce another concept of regular solution. It is extension of ideal solution towards the reality or real solution. So now we have to understand the variation of del H mix with the composition, and it is parabolic. If you go for the expression del H mix expression, then you will understand it is actually parabolic. Del H mix equals to tau into X and SD. And if you see in the picture that there will be a XA, some point XA equal to 0, and where pure some point XA equals to 0, where it is a pure B, and some point XB equals to 0, where it is pure A. So if we get the tangent at that 2 point, XA equals to 0 and X and 1, and if you want to relate them with the tau, it will directly go to the, when it got the corresponding axis, you will get the tau value. And if from the mathematical expression, you can understand very well. It is nothing very confusing. It is very realistic, and it mathematically can understand. But why it is parabolic? XA and XB can be represented by either of them. So XA equals to, you can write 1 minus XB. So scenario will be a quadratic scenario. So it will looks like a y square equal to 4x expression you can get, and then what you will get, that you will get the parabolic form of the diagram. I am going slow, then the voice will be good. Maybe it's an internet issue. No problem. Just I am going slow. Somebody is stating that voice is not clear. Okay. Now, if you see a scenario of a particular phase, regular solution model. In the ideal solution model, what is the difference between regular solution model and ideal solution model? In ideal solution model, that del G mix only depends upon the minus capital T del X mix. That capital T basically represent temperature in absolute scale. But in case of regular solution, which is the extension of ideal solution towards real solution, reality. So here you are also incorporating another term that is called del H mix, and del H mix is equal to tau XA and XB. Okay. Now for ideal solution, in the just second line or that expression I have given, for a particular alpha phase, XA into GA plus XB into GB RT in the bracket XA ln XA XB ln XB. So if you see in this expression, tau is interaction parameter, and it actually tells you things are in a scenario is an attractive mode of between two different atoms, or they are in the repulsive mode between two different types of atoms. And it's a multi-component system. You just have to increase the in the terms with respect to different element present in the solid solution. Now, if you see here, extra term is there. That is del H mix. Here directly I have written the expression tau XA multiplied by XB. So in the free energy change due to mixing for a regular solution, you can tell that the del H mix minus T del S mix, and the expression is tau XA into XB plus RT in bracket XA ln XA plus XB ln XB. That part actually indicating the configurational entropy kind of concept. Now, for exothermic solutions, what will happen? Del H mix will be less than 0, and so it leads to mixing, leads to a free energy decrease at all temperature. And when del H mix is greater than 0, the situation become more complicated, because then you have to find out the comparative role of T del S mix as well as del H mix. So this is a scenario. Then things are complicated. So we'll understand slowly today class regarding that. So first you should know that tau, if it is a negative, that means attraction. So attraction, okay, we understood. A will attract B atom. But what does mean? How it can be seen in the reality? It leads to compound formation. In any kind of phase diagram, if you see certain line compound or something intermediate compound and all those things, that actually the specific composition where interaction parameter is very negative. The attraction between two different types of atom present in the solid solution are very significant. Now we are going to understand when tau is positive, means repulsion, what it means, what it leads to. In the physics scenario, in reality, it leads to miscibility gap. Phase separation, two phases are going to separate. Okay, because A atom does not like B atom. They are having a repulsion. So now to understand this regular solution model, it is in extension of ideal solution to Earth's reality, but there also a strong assumption is there. What is that assumption in the regular solution model? Tau, that is the interaction parameter, is same throughout the phase diagram, because A part, and if you go end of the B part, where the A is 100%, B is 100%, throughout the phase diagram, you will be taking that, the tau is same throughout the phase diagram. This is a strong and significant assumption, and is a futuristic assumption for regular solution model. Now we have to understand that is it a reality that throughout the phase diagram, the tau is always same, the interaction parameter is always same, constant. It's not reality. Solubility of one element in other element is not the same always. A is more soluble in B. That does not mean that B also will be the good solubility, having good solubility in A. So the solubility concept from vice versa system, suppose A to B and B A in B or B in A are not always going to be same. If it is that, then how can interaction parameter will be same throughout the phase diagram? So this is also not so valid assumption with respect to practical scenario. So again, we have to extend the regular solution model to certain extent so that we can reach to close to the reality. If that the above statement, if you see, if it is a true, then tau is not same throughout the phase diagram. Already we understood. So now we are going to introduce sub-regular solution model. What is that? Now we are talking about the del H mix is equal to XA into XB multiplied by XA into tau A and XB into tau B. Now things are different. The tau A and tau B two different interaction parameter, and how it is going to contribute towards the del H mix, it depends upon how many number of A atom present and how many number of B atom present. Means what will be the mole fraction of A and B respectively. That will decide how tau A will contribute and how tau B will contribute towards the del H mix. Now again we have to check how from sub-regular solution concept to return back to the regular solution concept. What is the condition? Now if you check tau A equal to tau B, that is actually we are talking about few minutes ago. The assumption tau is constant throughout the phase diagram, then the solution is regular solution. Again, you can, if tau A equal to tau B, then it will come out and XA into XB, then you will understand that XN plus XB, it will be equal to 1. Then what will be the expression? Tau into XB, XA into XB. So that above sub-regular or solution model is not always work. Even this model also not going to capture all the real solution behavior. Why? Now, if you find in the phase, in the magnesium silicon phase diagram, if you talk, there is a strong possibility that interaction parameter represents significant attraction at specific composition, not a range of composition or throughout the phase diagram. In particular specific composition, that may happen and that may lead to a intermetallic compound. So line compound in the phase diagram, and such kind of understanding, if you want to know, you can refer magnesium silicon phase diagram. Next slide also we are going to discuss that part in a magnesium silicon phase diagram. If you see here, I have represented magnesium silicon phase diagram, and in the phase diagram magnesium to silicon one line is there, and that is very important. Why this line is occurring? In that line the attraction is very significant and highly negative, so that's why that line is there. So this kind of reality is not captured even by sub-regular solution model, although in reality we are seeing such kind of behavior. So what first we'll start with very basic thing, that is crystal structure. Magnesium having HCP crystal structure. So if you want to calculate the free energy of magnesium, so what you require? You require CP, and CP you have to calculate, and from the CP, from del H you can find out H equals to CP dt from certain temperature to certain temperature. If you integrate it, then you will get the H. And if you go for S, then Cp by T dt for condensed matter, again certain temperature to certain temperature. If in between there is no transformation of phases are there, then we can calculate easily the Gibbs free energy. And silicon has a crystal structure diamond cubic. Again, you can do that thing. But if a binary solid solution, there is a phase called alpha, and which are having a crystal structure HCP, and then you want to understand the Gibbs free energy of that, then what will happen? A is a magnesium, so Xa into TMG or TA, and A is magnesium, is alpha phase also HCP. So calculation of GA is not a problem because you directly can get, you know the CP, you can calculate for magnesium. But calculating the GB, the Gibbs free energy in the alpha, which is in phase, the silicon, for silicon is very difficult because you do not know the CP of silicon at HCP crystal structure, if it is present at all. Because you know the CP of silicon at when silicon is a diamond cubic crystal structure, but you do not know the free energy of silicon because you do not know the CP of silicon at HCP. So that is the biggest challenge to understand a particular phase, even for the binary, the free energy of, because you do not know silicon, if it is in the HCP structure, what will be the free energy, Gibbs free energy, that is. So then what we have to do, one has to try to calculate the free energy change like KG, silicon, FCC to HCP, diamond cubic to FCC, this kind of change of phase, then we can do. And in this regard, I am just giving an information. I am not going to so deep. This is a very advanced studies, and still people are doing that. That is called CalPHAT concept, calculating phase diagram, and it is depending upon the first principle based study. It is actually Schrödinger equation, electronic structure, and all those things. Density functional theory, people can do it. Not only density function, any first principle ab initio method, people can do the things or find out different crystal structure, what will be the free energy, and the concept is known as, very well known, the lattice stability, the lattice stability criteria. This part is there. I end up the subject. If somebody is interested, I can give a lecture on that. But this is the important part. If you want to get a Gibbs free energy for a different crystal structure, in which crystal structure you do not know the CP. So this is an important part. Now we understand that sub-regular solution model also not going to be valid. Even if very simple magnesium silicon binary phase diagram, we are finding that we cannot explain based on that sub-regular solution model. So we have to extend the concept to more reality. This is the demand. This is the demand of real physics-based cases where the solution model, even sub-regular, is not working. Now we are going back to regular solution and try to understand how different del G mix diagram will appear based on the positive or negative interaction parameter. So there are different values of tau. The interaction is may be positive, it may be negative. Based on the del H max will be negative. Based on del H max will be positive. Based on the interaction parameter. That is a very important parameter in order to understand the Gibbs free del G mix or Gibbs free energy for change for the mixing. So now we'll start with the understanding. Suppose you can see omega negative. What this means? It means already we understood attraction. That means formation of compounds. And omega positive means repulsion. And repulsion means this is called certain kind of what you tell that immiscibility or miscibility gap. And that leads to phase separation. So what I can call it as a miscibility gaps or phase separation, which end of the day or finally ends up into a phase separation. Already we are finding two cases. For negative, there will be a chances of formation of compounds, and for positive, there will be chances of phase separation. Now, if you will see, possibly we can
understand that what we have done, that we have assumed the interaction parameter is same throughout the phase diagram. For regular solution, we have to take the assumption, and based on that, we are going to understand the scenario. So from one end of the phase diagram to other end of the phase diagram, the interaction parameter is same, which is actually not always true. Already we understood from the concept of some regular solution. Then also we can go beyond that. So, and why it is not true? Now, if you see an example, if you can take an example of copper zinc, zinc dissolves in copper very much, whereas copper does not dissolve in the zinc. So A is dissolved in B is very well, but that does not guarantee that B is going to dissolve in A is very good, in a very good fashion. So we try to give a logic based on based on the valency. We used to give the valency, that Hume-Rothery rule and all those things. But if that is true, the interaction between A and B atom is different for one end of phase diagram to another end of the phase diagram. That we have to capture already in subregular solution model. We have captured that. Now, if you want to see that the delta H mixing, I mix up once in a while. Suppose delta H mixing, that is omega, XA and XB, if you calculate omega into XA into XB, that means if it is representing that, we are talking about two interaction parameter, one at A side and one at B side. And based on that, we can derive the regular solution. Now, in this, now we have enough understanding about regular ideal solution as well as subregular solution. Now we are going to understand how del H mix is can be plotted with respect to XA and XB, and how the trend will be there. So if you see, if you assume that in the picture that tau is negative, means there is a attraction is going on. So now if you go for the del H mix will be negative because tau is negative, and T del S mix never can be negative. We already discussed few class ago. So minus T del S, it should be very negative. And if you add these two things, you are going to get del H mix is negative. And if you consider the GA and GB and you are going to calculate the G alpha, then you will get such kind of curve for the Gibbs free energy. This is very simple and to get the things. But when it is a positive, the scenario totally different. When tau is positive. Now when tau is del H mix is positive and T del S mix is also negative. Now there we have to consider two cases where mod value of or magnitude of T del S mix is much higher than del H mix. Then what we are seeing in the scenario is, if it is reverse, if del H mix is much higher, then it will be upper side of the zero value, means is more positive value of del H mix. So there will be no mixing. So this is the very important section one should understand by statement that tau, when it is paired positive, then you cannot only rely on the tau positive value. You have to also consider what will the comparative value of capital T multiplied by del S mix and del H mix. You have to get that comparative value. Then only you can properly draw the G alpha, the Gibbs free energy for that particular alpha phase. Otherwise, you cannot. So in this way, you can understand that if the case is the mod value of T del S mix is greater than del H mix, then the end of the day, the Gibbs free energy curve will for the alpha phase is looks like that. Now, if you go for alpha positive and del S mix is less than del H mix, and if such scenario is much less than, then you are going to get such kind of curve. And why is it so? It may be just vice versa. It may start from low of G value to high, from G value to GA value to higher value, then come down. That may occur. So it is a why that particular shape is there. It is not. It can be just opposite inverted shape of this plot may occur. Why it is not? So for if you want to understand that, in order to understand that, what you have to do, you have to go for del G del XB. You just do derivatives, and you will find that at XA and XB in both cases the alpha, that is a infinity. Means if you go with respect to XA, when the X from one pure axis to the next towards the B direction, from A pure axis to the B direction, then always there is a decrement in the overall Gibbs range of the particular phase. So that is because if you go for derivative, and it will find out infinity, and it is a very basic mathematics, simple mathematics to find out where inflection point is there and all those things. From that you can understand. That's why this nature of the curve is like that. Now next slide, we are going to summarize certain cases. This is the actual cases of del H mix, d del X mix, and that represent del G mix when tau is much less and temperature is very high. Making temperature very high, you are actually enhancing the value of T into del S mix. And if it is less than 0, low temperature, then what is happening? The del S mix, if it is low, then since del H mix and del S mix are comparable values, then the length, the magnitude of del H mix is much less, but it is still in the negative side because tau is less than 0. And if tau is greater than 0 but high temperature, means del S mix is much greater than del H mix, then you are getting del H mix in the negative part of the schematic diagram. But here del tau is greater than 0 and low T, means T del S mix much lesser than del H, and initially you can see T del S is significant contributor, but slowly del H mix is increasing, so its contribution is more. So del G mix, initially it's negative, slowly get the point where the slope is changing, then again go to the higher side, and again you can get the lowering of the del G mix values. So in this way, you can represent the overall understanding of free energy of regular solution. So today class is over.